So yeah, good morning. So we will continue where I left, but I just want to make a quick announcement. The first assignment will be posted probably Wednesday or Thursday this week, so after the next class. And I think I've mentioned earlier that generally roughly 2 weeks to work on that and then turn it in. So all right. So in to the very end of the last class, what we were essentially just developing some intuitions of what is amplification of light, and the end result of putting a gain medium for light is to increase the intensity or the amplitude of the electric field or the magnetic field. That's a classical way of looking at it through Maxwell's equations. If you want to look at it in terms of purely quantum electrodynamics, it's increasing the number of photons. That's really what it is. Two ways to look at the same phenomenon. So today we'll finish this discussion. Look, I think we had developed this notion that if I can make a resonator for light to bounce between walls, and I could give to counteract the loss, if I could give some gain through stimulated emission, right, which amplifies the number of photons or the electric field, then I have a chance of making a laser. And I want to finish up that discussion and get started on the looking at the fields here in some more detail, outside the laser and also inside the laser. We'll look at it in some detail today. So one of the things I did not mention, we did discuss that if I have a two-level system, where the electrons, so the electrons could be in energy E1 or in energy E2. So it could be atoms in a gas, molecules in a gas laser, or could be the valence band and conduction band in a semiconductor diode laser, whichever be the gain medium for your laser, but you have energy levels as such. And then we're saying that we're going to excite them. We're going to create a population inversion, right? Thermodynamics would suggest that the number of electrons in energy 1 and number of electrons in energy 2, if we were to leave it to thermodynamics or equilibrium, what will be the distribution of energies or electrons in these two states, for example, roughly? Yeah, most of it would prefer to be in the lower energy level. That's right. But what would be the kind of, can we give a good estimate? Anybody wants to suggest an quantitative measure? Yep, Sam.
The ratio is to be a Boltzmann factor of
yeah.
that energy difference over kT.
That's right. So this is electrons being fermions. So actually, it does not matter what particles you choose, whether you are bosons or fermions. This expression looks like E2 minus E1 over Boltzmann constant Kb times temperature. So that's how it looks, right? And just so that I am not going to write down the expressions for Fermi-Dirac distribution for fermions or Bose-Einstein distribution. We had kind of written that for the blackbody radiation in the first class. But both of them at high energies, this is the tail for both. For Bose-Einstein condensate for bosons, which are photons, or for electrons or neutrons, protons, whichever, which are fermions. So this is the tail. And I think you can see right away that if you leave the system to a thermodynamic equilibrium, no matter how high the temperature, you can try to heat up as much as you want, right? Can you achieve population inversion here? It's an interesting question, right? Let's see. I mean, you should look at extremities. Let's take t to infinity. What do I get on the right hand side? 1, right? e to the power 0 is 1. That means the best I can do is n2 is equal to n1. I cannot achieve population inversion by just heating up this thing. Right? Not possible. Right? So obviously I have to do something else, right? And that's why I'm saying I'm going to optically excite it. And there are a couple of other ways to excite it. But what you have to really do, so let me kind of write it. Best at equilibrium is that, therefore, no population inversion and no laser, because there's no gain, right? So I have to do something else, and I have to basically find a way to pull this way out of equilibrium, because it's clearly upside down, so it's highly non-equilibrium situation. So I can shine light, I can pump it, or there are many other ways, your chemical reaction, electron injection, all kinds of things. But essentially you are trying to, let's look at the situation where I'm using light to excite it, to pump it, and I excite it this way, right? And then I try to do more and more. Let's have maybe 6, just for representation's sake, 6 here, and so I get 3 above. But now you run into another problem, and the other problem is quantum mechanics tells you that the rate at which you go up is exactly the same as the rate at which you come down. It does not discriminate. Quantum mechanics says that if you have a rate going from 1 to 2, it's exactly equal to the rate going from 2 to 1. Now, which one will happen depends on how much particles are there in that state, right? But the rate itself, the total probability of that happening is dependent, if you want to go from 1 to 2, is dependent on how many you have in 1 and all that. But the rate itself, the probability of that happening, there's no discrimination of going up or going down in quantum mechanics. Therefore, the best you can do now is you pump it and you put, maybe take 3 states from here, put them here, but now they are also trying to come down, right? So it turns out what you do is, initially obviously you have absorption. As you start increasing the number of photons, you're going to have absorption. Initially you will have absorption, so this is intensity of excitation. So you're having absorption, right? And then you also have, a part of it is spontaneously emitting. But essentially what I'm trying to say is the amount of, you will reach a certain point when both of them will become equivalent. By just pumping, you have reached the state of t is equal to infinity. But by optical pumping, obviously your temperature is finite. This is nothing has blown up or nothing has wrong has happened there, but you have reached that situation very quick with excitation. And beyond that point, if you excite it even more, it's called transparency. It's not going to do anything else. It's going to get stuck there again. Because the rates are exactly equal for going up and going down. And these things we're going to do it quantitatively in great detail, later in the course. I'm trying to get the whole message across initially. The main things that need to be ticked off to make a laser that need to work before you can make a laser. Right? So therefore, what's the way around it? You can't do this. You can't make a laser because of this bottleneck. So what do you do? Actually, the picture is right there. So you cannot do it with a 2-level system. You have to go to a 3-level system. So that's kind of the situation. And what you do there is you have another state here, and now you can have 2 rates. And now you can play with the rates. So you can have a rate of going up from state 1 to 2 to 3. So you have a certain rate of going up. You have a different rate of coming from here to here, and you have a different rate of going, you have the same rate of going from here to here. But essentially what you do is you excite this. This is empty. And then these relax here, and then you can easily get that N3 will be greater than N2. That you can get. It's possible. By playing with the rates. You have to choose the right atoms or the right gas or the right active medium, which will give you this gain, but you need this 3-level system to get it to this. If it's not very clear, because we are not doing things quantitatively yet, we will do it in great detail later. So, is that at least qualitatively acceptable? Yep.
Just to clarify, so the 2-level system, is it just very poor, or is it actually impossible?
The two-level system, from what we have discussed till now, from all the concepts we have discussed till now, it's impossible to get it. So it will reach optical transparency, meaning once you reach N1 is equal to N2, if you increase light further, the light will go through because there's nothing else to do. So it's transparent for that beyond a certain intensity. It doesn't absorb anymore. So it saturates in some sense. The absorption saturates. And then you can't get any beyond that, and that's why we need a three-level system. Okay, and minimum three-level. You can go for all kinds of other things, but minimum we need a three-level system. And this you're going to, I think there'll be a problem where you're going to prove it, and the proof is basically two equations, rate equations, which show that you can have N3 greater than N2 in the end. So, yeah. Yep.
What's preventing the N1 to N3 transition going back to N1 instead of N2?
Very good point. It does not. Nothing is preventing it, right? Very good point. Nothing is preventing it, but this rate can be much slower than this rate can be much faster. Does that make sense? So then you fill this preferentially over that. That's the game you have to play. So gamma 3 to 2. This is a rate. Will be much larger than gamma, 3 to 1 or 1 to 3. Both are the same. And then you'll run into another problem. You have to empty these out. We'll go into all those things later. But this is the minimum requirement. Okay, so the next thing I wanted to say is we had already developed a basic notion of this light oscillator in an analogy to a LC or electrical circuit oscillator, where you have mirrors, and then you have the light beam going back and forth, right, in between the two mirrors, and then that's your feedback. You're essentially bouncing light back and forth between two mirrors. And so that made your resonator or cavity, and then you needed, because of losses, you needed this additional element, which is the gain medium or amplifier, right? Gain medium, right? And we kind of discussed a little bit about it. So we said that, well, if the length of the cavity is L, or the length of the resonator is L, I know now how to find the frequencies. This is a quick recap. The frequencies look like some integer times c over 2L, where c is the speed of light and L is the length of the cavity, right? So 1 meter, we kind of had an idea, speed of light is 3 times 10 to the power 8 meters per second. Speed of light, you have maybe heard about it. It's not extremely large. It is obviously the highest that we can get, but it's in terms of ultra fast electronics and optoelectronics, it's not that fast. It's actually a limitation in many things today. So it's the popular way to remember it is it moves in 1 nanosecond. It goes only 1 foot, a foot per nanosecond. In 1 nanosecond, it goes that far. Right? And I think today electronics is going picosecond and sub-picosecond. So going that far, you cannot avoid. You don't have a nanosecond to do much logic because your transistors are very fast. They can do a lot of computations within a nanosecond, so because they switch in a picosecond. So light is also a limitation, though it's the fastest we can get today, right? So all right, so with the length L, we saw that there are these cavity modes or resonator modes, right, which are allowed. These are the half wavelength, integral number of half wavelengths that are allowed, right, where n is the number of half wavelengths of light that fit inside this L. If it's a meter, you're typically looking for visible light about 1 million or so half cycles, right? We talked about that. Yeah. All right. And then what we said is so these are all the modes possible, and now which ones do I want, which ones do I retain here is really dependent on my gain medium. Oh, sorry. The gain medium is going to help me select which ones. And let me draw 2 lines. One is a dashed line here. And these are, again, at this point, still qualitative. This is frequency. The dashed line here is, I'll call it the loss as a function of frequency. So I think you know that the moment I put anything here, if I put a glass window or anything of that sort in between the two, yeah, there's light incident, but there's also a little bit of reflection here, there's transmission here. I think you know that. Any medium, any discontinuity in refractive index is going to have a reflection and transmission. And we see today from Maxwell's equation, except for one case, we can actually prevent that. So that's called the Brewster angle. We're going to look at that. But regardless, so if I just take a plain glass window, typically there's about a 4%, right, reflection. 4% is reflected and the rest is transmitted if you are kind of normal incident. I mean, obviously if you go at an angle, you can see much more reflection, right? So, and things like that. But similarly, so there's more loss out here. The mirrors may not be perfectly conductive. There may be some skin depth and therefore some loss there, right? Some loss here. And all these things we're going to look at today from Maxwell's equation perspective. Right? But right now, what we want to discuss is there were a few questions towards the end of the class, or maybe even after the class last time. So here's the loss. If I kind of make a simplifying assumption that the loss does not depend on the frequency or the wavelength of light, that's how it looks. I mean, yeah, it may have some variation. It may depend on the wavelength and all that, but let's just simplify it. And then you have the gain, and the gain medium will have its own spectra. So alpha here is the loss. So you can call it alpha, and the gain will have its own spectra. And let's say I start with a very low level of pumping, and my gain is just like that. The gain at all frequencies at this stage is lower than the loss. So I'm losing light. I can't laser. There's no laser. No, the gain has not overcome the loss. So, but as I pump it more, and I have a 3-level system, done all my design, I made my 3-level system for the active region, and I pump it more and more. And at some point, this gain curve is going to, basically as I pump more, the gain curve is rising. What does that mean? I'm going more and more towards population inversion. I have N3 more than N1. So that's what I'm doing as I pump more, right? And the gain curve is kind of moving up, right? As it moves up, at some point, I think you can see it'll go above, and here, the one sketched there, maybe it's looking like that now. Right. So here's your window, then, over which you can now, the modes inside that window are the ones that can be amplified and will survive and the others will die out. You'll lose that, right? They won't survive. Is that clear? So these are the ones that will be selected out, and then so what you'll and if you remember, the other thing we mentioned is so typically what will happen is you will get a multi-mode sort of lasing. So there'll be a very sharp mode and a very sharp mode, and then so there'll be 3 modes, and the others will not exist. And now so you have a 3-mode laser. This is a multi-mode laser. All 3 modes can survive. But many times you don't need a 3-mode laser. Many applications to do with communications or some precision timing and all, you don't want multi-modes. You want single mode typically. Then the question is, how do you select one? How do you select one mode? And things like that. And there are many tricks for that, many tricks. And we are going to actually talk about those aspects today, after I finish this review. So as you can see, that if I don't let my gain go that high, if I am just at the threshold, right? If I lower my gain, then obviously I can have a selection of one mode. But you can see that's not the best strategy, because I want as much power out of my laser too. But that's one strategy. If you want one mode, lower the gain, and you have only one mode inside that window, right? But that's not the best strategy. So you want to be a little better than that. So what you can do, there are many ways to do it, but let me just suggest a few, and these things we'll obviously talk in great detail later, but at this point we are going to suggest, I'm going to just suggest a few. So you can keep this mirror fixed, but you can move this. You can move one of the mirrors and you change the L. right? You change the length of the cavity or the resonator. What does that mean? It means you're going to move these around, right? And by careful engineering, you get your gain to a point, and then, if you are careful, you can actually push out. As you can see, as you change the L, multiple things will change. The spacing will change, but so will the center frequency will also change. So it will kind of move to the right and then also stretch out, and that's what's going to happen with hits. But you can kind of play that game. You can make it have only one mode within that window if you kind of stretch out and move out all the other modes here. Does that make sense? As you change the L, the length. And so that's one way to select one mode. But as you realize right away, that is also a very nice way to make a tunable laser. A tunable laser. So you have selected one frequency. Let's say you have somehow pushed out all these modes because of the length or the cavity pushed them out. But now you still change it, and this thing is going to move around. Right? It's going to move around because it's still responding to the change in the length, cavity length. And therefore, this is a very nice way to also make it tunable. And tunable lasers are very important because, as you know, you can transmit data or whatever at one frequency, 1.55 micron, maybe 1.53, 1.54. You can have multiple channels if you can tune it fast enough. Right? So, does that make sense? I mean, it's like different lanes in a highway. I mean, you can have different data rates going through different. So tunability is very important and nice that you can do that. So the other thing I want to say here is this is typically not the best way to select out single modes. A better way typically would be if you're very, so maybe I can ask what would be a better way to kind of select out wavelengths instead of just moving this here. I can do something else. Yep. Take a guess. You said filter, or somebody said filter. Yeah, I mean that's exactly right. I mean you can add another filter. One is what will be called an echelon, which is essentially you add another little mirror, but we are going to add it at not a mirror, but a transmission layer, which has an optical length of much smaller than the bigger cavity length here. That's L, but this is a little a, right? You can add that. It's called an echelon, and you get some Fabry-Perot interference here. So now what you have is you have kind of two periods. You have a period there, and you also have a little period here. And so there are two periods that are going to go beat against each other. And so what happens now is the bigger cavity gives you these modes, and the smaller cavity, as you know, this is C over 2L. And the smaller cavity gives you much more widely spaced modes, where this is C over 2A. And if you're lucky, and if you do, I mean, essentially it's kind of a vernier. If you might, you can kind of select out that there's only one mode where both of them meet. You can select that out, right? So that's another way of doing this. So it's an echelon method. I'm just pointing this out because I want to motivate why do we want to spend so much time on Maxwell's equations and understanding light and reflection and all that. Here's one example. The other thing you could do, which is kind of neat as well, is instead of doing that, you can take, going back to Newton, you can put a prism, right? And maybe you have 3 or 4 different wavelengths coming in, and I think you know right away that if there are 3 or 4 different laser lights coming, they're going to split in real space. Split, right? And when they split in real space, you can take this here and put a mirror such that only one of the modes is going to be reflected back into the cavity. The others are filtered out. And only one of them goes back. Right? You can do that, right? This is nice. So this would be called kind of a Bragg reflector, right? And you can rotate it and select which mode you want, or the mirror. You can do all that kind of nice, fun stuff. You see, I mean, you are kind of spatially filtering it out by real space movement. You're filtering out all the rest other than one mode. So, is that, that makes sense? Okay. So tunability, there are many other ways. For example, let's say you're using certain, so you have two modes, and then you have one of them. If you have multi-modes, typically the next nearest modes are of different polarization, and we're going to talk about that. So you may have, and so you can use a polarizer to select out few modes, and many ways to do that. Okay, so the second thing I want to say is sometimes in some applications, and this is becoming increasingly kind of important, in some applications you actually use the multi-mode feature. And let me explain what that is. It's getting a little messy here. So here, instead of instead of selecting out just one mode, let's say I had multiple modes of light that are lasing. Let's say just two. Let's say just two modes are lasing, and this is frequency. So I think actually let's just look at one mode. If you have one mode lasing and you look at the time domain, I think it's very clear you have a pure sinusoid. It's pure sinusoid, right? So electric field is doing that, right? Now I add another mode by maybe stretching out my gain curve. My gain curve was initially like that. Now I've stretched it out to make it like that. Now I have two modes inside. What happens to this time domain in terms of electric field amplitude? You have two frequencies. Right? So how does the signal look now if I have two frequencies? So, yeah, please. Yeah, the sum of sinusoids. So it's called, it'll basically have one which is maybe a higher frequency and the other a lower frequency. So you may have another one that may be a lower frequency. So there'll be beats now. So they go against each other, right? So if I were to plot it a little more vividly in time domain, it will kind of have an envelope of the slower one, right? And within it will be the faster one, also kind of beating like that. Beats, right? So what's the separation of these peaks here in time? If separation here is delta F, which is C over 2L for you, right, for the cavity, the separation here is 1 over delta F, roughly. Give or take 2 pi, I'm just, right, in time domain. F1 minus F2. So again, if both frequencies are the same, this is infinite, so there's no beats. Right? So now what if I expand it even further and have another mode now? So as you can see, it will start having more, there'll be more now, right? There'll be multiple beats, and I can have 4 and 5 and 6. What happens to this? As you know, this thing is a Fourier transform of that, right? So in the end, if I have a very wide gain spectrum, and then I let a lot of modes go, what happens to the time domain? So this is a trick if you probably remember. So if I have, as you know, if I have a delta function, the Fourier transform is a flat, constant, meaning, the oscillations, but amplitude squared is a constant. But if I have what's called a Dirac comb, or a train, Dirac train, delta train, what's the Fourier transform of that? So it's actually also a series of pulses. So if I have maybe 5 of those, let's say, or 6 of those, what it's going to look like is a very sharp pulse with a little ringing sync function like thing, and then this is how it's going to look. I'm plotting now the intensity. I think you know that it'll go a little negative and all that too, but this is how it's going to look. So what's going on with this laser is you have multiple modes. Let me just also say that the separation here is 1 over delta F, but the width of this thing here is 1 over, if I have n modes here, then it's 1 over n times delta F. If I have multiple modes, this can be extremely sharp. very sharp. How sharp? In time domain, you can get down today to 10 to the power minus 15, so nano, pico, femto, right? Seconds, femtosecond. And I think some people are also have managed to get into attosecond here. So these are the shortest time scales that we can achieve on any device that we can make today. So what are we doing here physically? This laser is dumping all its energy in a very short pulse of a pico or femtosecond. All the energy, this is the electric field intensity, or magnitude of electric energy is proportional to that, and it's coming in a train of megahertz, or C over 2L roughly is megahertz. So, but the pulse width is extremely narrow. It's a very, very short pulse. So that's another thing you can do with multimode. But you have to ensure that all these modes get going, when they oscillate, they get going at the same time. If they're out of phase, then you're not in luck. Then what will happen is it is going to go down, it will broaden, and the pulse will not be ultra sharp. And to do that, we are going to talk about that later. How do you do that? But as you can see, the word used is you have multiple modes and you have to lock their phases. So this is called a mode locking. It's a mode lock laser. So you have a lot of modes going, but all of them are locked to the same phase. And when you do that, you can generate some of the shortest pulses that we can do on Earth today. Or a lot of energy instead of going in as a DC, as you do in a single mode laser. It's going in very short pulses. The same amount of energy, but going in very short pulses. So as you can see, what you can get then is, instead of maybe a milliwatt here, a milliwatt of energy steady state, you can have a megawatt, but in a femtosecond. If you want to dump a lot of energy in a very short time, this is a good choice. Right? And not only that, it also lets us probe now some of the fastest phenomena that occur in nature. So a relaxation of electrons by colliding with lattice. These things are very, very fast, occur at picoseconds and all that. There is no way to actually measure them directly, but now with this sort of femtosecond time scale, you have a clock which is ticking at femtoseconds now. Right? This is a very, very short time scale, so it also helps us measure and understand physical phenomena at that time scale. Right? And then there are all the other applications in nonlinear optics and all this kind, because the energy is so high that you are looking, it's highly in a nonlinear regime. Dielectric constant is not really a constant anymore. Things are changing. So you have nonlinear optics and all that really benefit from this mode locked, ultra fast laser pulses. Okay, so qualitatively, okay. All right. So the next thing I want to kind of say and lead into. Let's use the other word. And now lead into the next topic, which is understanding the Maxwell equations and such, is the fact that if I take a laser and let's say I have a beam that the laser beam comes out, I have made, so here's my box. I've done all my nice design, chosen my cavity or the resonator, gain media. Maybe I've used a Bragg reflector to choose out one wavelength and all that. And out comes the laser light here. Right? Now the question is, for example, let's say the diameter of this light is d, the beam. Now we can ask questions like, what is the amplitude, intensity of light? Is it uniform across this diameter? Is it more like a Gaussian? How does it look? We can kind of talk about those things now. The intensity of light. Right? If it's a single mode, if it's a multi-mode, you'll have multiple peaks and such things. We're going to talk about those things. But the more important question I want to start with and motivate, why do we want to understand or spend so much time looking at electromagnetic theory and Maxwell equation, and specifically things like divergence of an electromagnetic wave. If you emit it at a certain wavelength, how much does it diverge? Right? So if you have a single mode light coming out, what we are going to show now is if you let it go, right, there's always a little bit of divergence, right? So there's always a little bit of divergence. And this you cannot avoid from uncertainty principle. Any wave is always going to have a divergence. The laser in my hand, the beam spot that you see there is not the beam spot that came out from here. It has diverged. Right? In fact, if you take about the diameter, so what we'll show that is for a single mode laser, the divergence here, or the angle at which this starts diverging, is of the order of wavelength of the light divided by the diameter. We're going to show that now. Well, hopefully, right? Wavelength by the diameter. And the diameter of a laser pulse, light beam would be maybe about, I don't know, millimeter or a few millimeters. Wavelength depends on the color and the mode that you have selected. But as you can see, it really does not depend on what you made the laser with, what material you have chosen. So it's actually a fundamental limit, in some sense. There are, things where you're saying you can go sub-diffraction these days, but this is really a fundamental limit. And what we're going to show now, it's a very, very small angle. If your diameter, just for argument's sake, this is a little bit of a large size laser, 1 centimeter. And let's say we are looking at green light, or we are looking at 500 nanometers, and you can see the angle will be very small. So if you take this laser, how small is the angle? So if it's 1 centimeter roughly on the Earth, and you shine your laser all the way to the moon, it diverges. And its diameter by the time it reaches the moon would be maybe 50 kilometers or so. And it's obviously huge, but you realize the distance between the Earth and the moon is also very, very big. And now people use that for imaging lunar surface by sitting here on Earth. You can actually, kind of scan your laser and image things on the moon, and it actually bounces back. So that's really a very, very sharp beam. And it keeps being sharp for very long distances, certainly at the length of an optical table or a semiconductor circuit or whatever. It remains like a, that's why what we do is called a ray tracing. We're going to just trace it as a line. Right? That's what. And the second thing is, so this is true for gas lasers, for where you have these external cavities. External cavity meaning mirrors are outside and all that. And that's when you can achieve very sharp beams like this. The other family of lasers today, which is extremely important, is a semiconductor laser, where you actually take a piece of semiconductor PN junction or a PN diode, put some quantum wells or quantum dots or whichever way you like, and then you inject electrons and holes, and out comes from the side the laser beam from the semiconductor. This is a semiconductor laser. You get a PN junction, inject holes and electrons, create your 3-level system, population inversion, get light out. Here the waveguide is typically kind of the semiconductor material itself. And in a semiconductor laser, the angle is actually terrible. This angle at which it comes out is about 50 degrees or so. It comes out as a large cone. But it's a laser, it's not a LED. If it's a laser, no matter how much it is diverging, you can pull them all back again and make it a collimated beam. That's the beauty of the laser. That's the real beauty of the laser, that if your beam is going this way from your source of the laser, right, you can put a collection of lenses or things like that, and then you can redesign the laser such that it actually comes out as a collimated beam of any diameter you desire. Does that make sense? This is something you can do with a laser. Why? Because these wavefronts are completely coherent. If it was a light bulb, we can't do this. And it's not possible to do this with a light bulb or a LED. You cannot collimate it. Why? Because the phases in a light bulb are going all over the place. So you cannot, essentially in a light bulb what happens is you'll have, something like that, and you'll have something like, so essentially the distance over which you can do this is dependent on the size of the light bulb and the focal length and all these other things. For a laser, it depends on nothing other than the wavelength and the diameter of the beam. Doesn't matter what's your focal length and all that stuff. So that's something. So indeed, what I'm holding in my hand is a semiconductor laser. The light is coming out in a cone in 50 degrees, but there are a couple of lenses that are making this happen. So this is something you can do with a laser, and that's the nice thing about the laser. Okay, so I think that's all for. I didn't talk specifically about another very important property, which is the coherence, but we will talk about that in some detail. I want to get going on understanding the light beam itself. Just to summarize the whole thing, here's an example of a laser. This is a problem in your book. It comes much later, don't get worried. This is not going to be in your first assignment, but so essentially it's showing some typical diameters and length scales, choice of atoms with the 3-level system, but all of that stuff is inside here now, you can see. So here are the mirrors separated by half a meter. Here's the gain media, which is the laser cell, and inside it are these atoms, which have these energy levels. And now the question probably is asking you, well, here are your reflectivities, transmission, all that. Find me something, laser threshold, what frequency, and all that sort of thing. So that's an example. So it kind of synthesizes all the things we talked about till now. Okay, so the last thing, obviously, I kind of just to remember, just like any oscillator in electrical circuits too, the main thing about the laser is the net gain in a round trip must be greater than 1. That's the only way you can have lasing. Otherwise, you're going to die, right? I mean, the laser intensity will die. And that's kind of the most important thing, and we'll see later when we want to find the threshold for optical pumping or electrical pumping. This is the equation which you use. No matter how many times you reflect and transmit, you just have to keep track of all of them. Every time you multiply all the gain with all the loss, the product should be greater than 1. That's what there is, and Okay, so and now we are going to talk about electromagnetic theory and start looking at things like beam divergence. When can you actually achieve perfect transmission? Here's a great example of, pictures at least. If you have light going through and there's a certain angle and a certain polarization of the light, you will have complete transmission and no reflection. So that's the Brewster angle, and many of the gas lasers typically have this mirror, the Brewster, optical ports, if you might. So they're at an angle. And this happens, and all this thing we can now start looking at electromagnetic theory to understand. So I'm going to stop discussing now the basics of a laser. I'll come to this. I mean, there's many kinds of lasers and all that, but I want to get started now on electromagnetic theory. Just to get started today, and on Wednesday we will hopefully answer both questions and more. We'll calculate the divergence of any light beam as it goes through space, and then we'll also look at the Brewster angle and derivation of those things. So now we are moving on into chapter 1 of your book. So please read it, and let's get started. I'll just give you a summary. Sorry, a busy slide, but Maxwell's equations tell us how the intensity of light that comes out of the laser, which is composed of an electric field and a magnetic field, it tells us the laws of motion for these. How do electric and magnetic fields move? How are they created? How do they move? Basically, this is Newton's law, but for electric and magnetic fields. Right? That's Maxwell's equation. Right? So I'm going to now trust that you have a reasonable exposure to this. Now, in this part of the review of, it's almost a very short crash course on Maxwell's equations, but if you run into any trouble, please spend time with me, because this is rather important. Get this done properly. But okay, so essentially what we have then are two fields that we want to track in space and in time. That's really, that's really what light is. You have electric field and magnetic field, and how they move in space and how they oscillate and change in time is what we want to track. Right? So space and time. And so Maxwell's equations, typically, I think you might have seen, I'm going to write the differential form of Maxwell's equations. So if you have electric field, then the electric field, this is electrostatics, is always caused by some charges somewhere. In electrostatics, if I have a charge sitting somewhere, positive charge is going to radiate out from it field lines, electric field lines. It's going out. Right? So divergence, so electric field lines are diverging from a point charge. So, and mathematically you write that the divergence of the electric field is equal to the charge, but here you write it as a charge density per unit volume, coulombs per centimeter cube, coulombs per meter cube, whichever way. And so actually the way it's written, you have also a permittivity of vacuum here, or permittivity of the material, and this is typically consumed, this epsilon naught is consumed here and written as a divergence vector D, right? Sorry, displacement vector D. That's the way to write the electric field. You can write it in terms of electric field too, right? So electric field will be, epsilon 0. But physically, at least you see in this equation, what is divergence? Del over del x plus y del over del y plus z del over del z. Right? This dot product with whatever is your vector field here, right? Term by term. You find your x component, y component, z component, take a derivative of the x coordinate, y coordinate, z coordinate, add them, that's divergence, right? That's mathematical way of looking at it. Physical way is very clear. Field lines are diverging from here, going out. Right? That's positive divergence. They're coming in. This is negative. Divergence is negative. Okay? It's a sink of field lines. Here it's a source of field lines. Right? In this Maxwell equation, there is no time. That's why it's called electrostatics. Right? This charge is just sitting there, and it's just radiating electric fields, and that's the end of the story. Not quite, but at least in first thought, right? And you can see that if it's sitting here, and if you're an observer and you're moving, then that charge is moving with respect to you, right? So and that's what led Einstein, obviously, to realize that so a point charge sitting at rest is at rest with respect to the person sitting on it, but if the person is moving, then that charge is moving. And when a charge is moving, it's a current, and that creates a magnetic field. So electric field and magnetic field depends on the observer. What do you call what do you call a static electric field, and what do you call a static magnetic field? Depends on who's looking at it. But essentially, for electrostatics, you can see that if I have a point charge, it's going to create constant electric fields. If I have a constant current, it's going to create a magnetic field that wraps around that object, right, around which it's flowing. And so the equations then look. So that's divergence of electric field. What is the divergence of magnetic field? It's till today at least it's 0, because nobody has discovered yet this magnetic monopole, though laws of quantum and gravity do not rule it out, the existence of magnetic monopoles. But in our course, we're going to assume they don't exist. So now curl. Both of these are electrostatics. There is no time. There is no d over dt in those. So now we get into time-dependent phenomena where we look at curl of electric field, and that's negative rate of change of magnetic field. Right? And curl of magnetic field is the conduction current plus rate of change of the displacement, which is epsilon times E. I'm going to look into this in a little more detail, but those are the two time-dependent Maxwell's equations. So this is called Faraday's law and Ampere's law, of the people who first realized them. And Ampere had only found till here, and this was Maxwell's contribution, displacement current, because without it, these equations violate charge continuity and all that sort of thing. But these are the 4 Maxwell's equations. And now what we're going to show now is if you combine these two, out will pop from here the wave equation, which will tell you that light should be moving at 3 times 10 to the power 8 meters per second from the time-dependent fields. Physically, what is it saying here? That if I have a magnetic field that's changing with time, I'm creating electric fields. Forget about the curl for a second. It just says that the direction of the electric field is curling around the magnetic field. And if I have a time-varying electric field, I'm creating a little bit of magnetic field. I think you can see right away, if you let it go, if you first create a time-varying magnetic field, it's going to create electric field. So if that's what you do in an antenna. Your cell phone, you say make a call. You have a battery that's going to have all the metal strip around your cell phone. That's an antenna. The battery is going to go in, slosh the electrons back and forth. Now, you move the electrons back and forth at we're using 4G network today, so 4 gigahertz. That's the speed at which they're going. And then because electrons are being sloshed back and forth, it's going to create a little electric field around. But there's time varying. And as a result, there's a magnetic field that curls around the electric field. So essentially, as you can see, it will create each other, and you can turn essentially this will therefore sustain each other, and then that's the electromagnetic wave. That's light. That's great. Right. So that's the idea, so that's not a coherent source. That's not a laser, but it's still light. And 4 gigahertz is light we cannot see with our eyes, but obviously if you had the right, detectors, you can, right? So now, okay, so what we'll, I think I'm a bit out of time, but let me just say that what we are going to first do is look at the time-dependent Maxwell's equations, and from there we'll pull out the wave equation for light, right? And then we'll show that the electric we can write the electric field and the magnetic field in a certain way. And very soon after that, I'll essentially just want to go to this point that we'll see that the laser light that comes out, if it's going in this direction, in the perpendicular direction to it, there's a little spread to it. This is a Gaussian beam. And then if you want to make it more focused in this direction, it will spread out in k-space. If you want to make it plane wave, it will be sharper in k-space. And because of such things, you will have a divergence, and we'll calculate the divergence, show that it's wavelength over the diffraction limit. It'll come out of Maxwell's equation very nicely. So we're going to see that next class. And then we'll start seeing Brewster's angle, at what polarization can you have no reflection at all transmission and all that. So it'll all come out from Maxwell's equations. All right, so let's meet Wednesday, and we'll continue in this topic.